Section: Introduction. Let's dive into the fascinating world of information theory and machine learning, two fields that are deeply intertwined. They're so closely related that some even describe them as two sides of the same coin. One of the most beautiful connections between these fields is the relationship between probabilistic data models and lossless compression. This relationship is best explained by the source coding theorem. In simple terms, this theorem states that the average length of a message, when optimally encoded, is equal to the negative log base 2 likelihood of the statistical model. This means that if we maximize the log base 2 likelihood of the data, we minimize the number of bits needed per message. There are many ways to achieve lossless compression with a probabilistic model. Some of these methods include Huffman coding, arithmetic coding, and asymmetric numeral systems. Among these, arithmetic coding is known to be the best in terms of coding length. This means that the overall performance of the compression depends on the capabilities of the probabilistic model. In recent years, large pre-trained transformers, also known as foundation models, have shown great success in a wide range of predictive tasks. This makes them promising candidates for use with arithmetic coding. In fact, transformer-based compression with arithmetic coding has produced top-tier results in both online and offline settings. In the online setting, a model is trained directly on the data stream that needs to be compressed. In the offline setting, which is the focus of our work, the model is trained on an external dataset before it is used to compress a different data stream. This means that offline compression is performed in context, with a fixed set of model parameters. Transformers have shown impressive in-context learning abilities, which makes them ideal for offline compression. However, as we will discuss, transformers are actually trained to compress well, which means they must have good in-context learning abilities. The context length, or the maximum number of bytes a model can compress at a time, is a key limiting factor in offline compression. Transformers can only compress a few kilobytes at a time, while requiring a lot of computational power. Many challenging predictive tasks, such as algorithmic reasoning or long-term memory, require long contexts. Therefore, extending the context lengths of these models is a key challenge that is gaining increased attention. In this work, we propose using lossless compression to study foundation models. We conduct a thorough empirical investigation of the offline compression capabilities of large language models. These models have recently become readily available and can be used for compression without the training overhead. We show that these models, while primarily trained on text, also achieve top-tier compression rates across different data modalities. They use their context to condition a general-purpose compressor to excel at a particular task. We also shed new light on scaling laws, showing that they hold true for compression. However, measuring the compression rates instead of the log loss adds a twist. Scaling beyond a certain point will deteriorate the compression performance since the model parameters need to be accounted for in the compressed output. We also propose viewing prediction through the lens of compression, as it encompasses generalization. A model that compresses well generalizes well. Our contributions include an empirical investigation of the lossless compression capabilities of foundation models. We show that foundation models, trained primarily on text, are general-purpose compressors due to their in-context learning abilities. For example, Chinchilla 70B achieves compression rates of 43.4% on ImageNet patches and 16.4% on Libri speech samples, beating domain-specific compressors like PNG or FLAC. We provide a new perspective on scaling laws, showing that the dataset size provides a hard limit on model size in terms of compression performance. We use the compression prediction equivalence to employ compressors as generative models and visually illustrate the performance of the underlying compressor. We show that tokenization, which can be viewed as a pre-compression, does not generally improve compression performance, but allows models to increase the information content in their context and thus generally improves prediction performance. In the next section, we will review the necessary background on information theory and its relation to likelihood maximization. We will consider streams of data of length n from a finite set of symbols. We will denote the empty string as epsilon and the concatenation of two strings s and r by senior. Section summary. Information theory and machine learning are closely connected, with probabilistic models of data and lossless compression being essentially equivalent. The source coding theorem states that the expected message length of an optimal entropy encoder is equal to the negative logarithm of the likelihood of the statistical model, meaning that maximizing the likelihood is equivalent to minimizing the number of bits required per message. Large pre-trained transformers have shown promise in achieving state-of-the-art compression results, but their context length is a limiting factor, and extending it is a key challenge. Section: Coding distributions. Let's talk about coding distributions. A coding distribution, denoted by ρ, is a sequence of probability mass functions. These functions map sequences of symbols to probabilities between 0 and 1. For every natural number n, the probability of a sequence of symbols is equal to the sum of the probabilities of all sequences that can be formed by appending any symbol to the original sequence. We start with a base case where the probability of an empty sequence is 1. From this point forward, we'll drop the subscript on ρ when its meaning is clear from the context. Under this definition, we can calculate the conditional probability of a symbol given the previous symbols in the sequence. This is done by dividing the probability of the entire sequence by the probability of the sequence without the last symbol. This leads to two important chain rules. The first rule states that the probability of a sequence is the product of the conditional probabilities of each symbol given the previous symbols. The second rule is similar but applies to a subsequence of symbols. Now, let's move on to lossless compression. The aim here is to convert a sequence of symbols into a binary code of the smallest possible length, while ensuring that the original sequence can be perfectly recovered from the binary code. To achieve this, we use a binary source code that assigns a binary code word to each possible sequence of symbols. The length of this code word is measured in bits. Our goal is to minimize the average number of bits per sequence. This is done by assigning more bits to rare sequences and fewer bits to common sequences. Shannon's source coding theorem tells us that the minimum average number of bits per sequence is equal to the Shannon entropy of the coding distribution. Arithmetic coding is a method that constructs a code with a length that is almost optimal. It links coding and compression with prediction and modeling. If we assume that we can perform arithmetic operations with infinite precision, the length of the arithmetic code is one bit more than the negative ceiling of the logarithm of the probability of the sequence. The optimal code length is the negative logarithm of the probability of the sequence. In practice, we can only perform arithmetic operations with a finite precision, which adds a small number of bits to the code length. However, this number is negligible for 32 or 64-bit arithmetic. The arithmetic code of a sequence is the binary representation of a number between 0 and 1. We find this number by gradually narrowing down an interval that contains it. We start with the interval from 0 to 1. In each step, we divide the current interval into subintervals, one for each possible symbol. The size of each subinterval is proportional to the conditional probability of the corresponding symbol given the previous symbols. To encode a symbol, we continue with its corresponding subinterval. Finally, we choose the number in the last interval that has the shortest binary representation and use its binary representation to encode the sequence. Decoding a sequence from its arithmetic code is straightforward. We start with the interval from 0 to 1. For each symbol in the sequence, we find the subinterval that contains the arithmetic code and decode the symbol that corresponds to this subinterval. We then continue with this subinterval for the next symbol. Section summary. A coding distribution is a sequence of probability mass functions that satisfy certain constraints, and it allows us to calculate the conditional probability of a symbol given previous data. Lossless compression aims to encode data into a minimal bitstream length while ensuring recoverability, and arithmetic coding achieves almost optimal length by connecting coding and compression with prediction and modeling. The arithmetic encoder narrows down an interval to encode each symbol, while the arithmetic decoder decodes symbols based on the interval and probability distribution. Section: Likelihood maximization. In the real world, we often don't know the exact source distribution, denoted as ρ. Instead, we estimate it using a model, which we'll call hat ρ. This means that instead of getting the optimal code length for a sequence, we end up with a slightly longer, suboptimal length. This suboptimal length is what we call the cross entropy. So, if we want to minimize the length of the encoded data, we can do this by minimizing the cross entropy. This is the same as maximizing the likelihood. Interestingly, this is the same objective used to train current foundation models, using what's known as the log loss. So, minimizing the log loss is the same as minimizing the compression rate of the model. Just like we can use a predictive distribution for lossless compression, we can use any compressor for sequence prediction. The main idea here is to define ρ as the coding distribution, where the length of the sequence when encoded with a compressor is used. We've talked about optimal coding with respect to data sampled from a fixed distribution. But what about universal coding, which is optimal for all possible sampling distributions? In theory, we can achieve this by choosing the length of the sequence as the Kolmogorov complexity, which is a measure of the computational resources needed to specify the sequence. This gives us a conditional distribution that is universally optimal. The Solomonoff predictor is a Bayesian mixture of all predictors that can be programmed in a chosen Turing-complete programming language. For a predictor of a certain program length, the Solomonoff predictor assigns a prior weight to that predictor. If we have a set of all predictors that can be programmed and computed, the Solomonoff predictor assigns a probability to a sequence. Therefore, compressing optimally is equivalent to predicting optimally and vice versa. Now, let's talk about our evaluation of the compression capabilities of foundation models. We compared our language model compressors to two general-purpose lossless compressors, gzip and LZMA2, used by the 7-zip software. Both are based on Huffman coding and the Lempel-Ziv-Welch algorithm. We also considered specialized lossless compressors for image and audio data, such as PNG and FLAC. We evaluated these compressors on datasets of 3 different types: text, image, and audio. All our datasets are 1 GB in size. We had to consider the different context lengths of the compressors. Transformers are restricted to short contexts, while gzip uses a maximum context of 32 kilobytes, and LZMA2 has a virtually infinite context length. For compressors with finite contexts, there are 2 approaches to compress sequences that are longer than the context length: sliding the compressor byte by byte, or chunking the data stream into sequences and evaluating the in-context compression averaged across batches. For transformers, we used the latter approach. We divided all datasets into sequences of 2048 bytes and fed them to the compressors one by one. However, since classical compressors usually include a header in their compressed output, which can be larger than the compressed data in some cases, we only counted it once for all batches. We also reported the compression rates of classical compressors on the unchunked datasets. Section summary. In practice, when the source distribution is unknown, it is estimated using a probabilistic model. This leads to suboptimal code lengths and the use of cross-entropy as a measure of expected length. The objective of minimizing the cross-entropy is equivalent to likelihood maximization, which is also the objective used in current language model training protocols. Section NWIC 9. We're going to discuss 3 different datasets: NWIC 9, ImageNet, and LibreSpeech, and how we use them to evaluate our model's data compression abilities. The NWIC 9 dataset is a collection of the first 1 billion byte from the English Wikipedia XML dump as of March 3, 2006. It's an extension of the NWIC 8 dataset, which only contains the first 100 million bytes. We train our basic transformer models on NWIC 8, but we test them on both NWIC 8 and NWIC 9 to see how well they can compress data that they haven't seen before. Even though NWIC 8 is part of NWIC 9, it only makes up the first 10% of it, so there's still a significant difference in the data distribution. The ImageNet dataset is a collection of over 14 million annotated images from the WordNet hierarchy. It's been used since 2010 in the ImageNet Large-Scale Visual Recognition Challenge, a benchmark for image classification and object detection. We take continuous patches of size 32 by 64 from all images, flatten them, convert them to grayscale, so that each byte represents exactly 1 pixel, to get samples of 2048 bytes. We then combine 488,821 of these patches, following the original dataset order, to create a dataset of 1 gigabyte. LibreSpeech is a collection of around 1,000 hours of 16 kHz English speech. The data comes from audiobooks from the LibriVox project and has been carefully segmented and aligned. We divide the samples into batches of 2048 bytes and collect 488,821 such batches into a dataset of size 1 gigabyte. We compare the compression rates for all compressors and datasets. We look at both the raw compression rate, which doesn't consider the model size, as well as the adjusted rate, which does. The size of the Python program for classical compressors is very small, a few kilobytes at most, and thus barely affects the compression rate. However, language models have a large size, which significantly reduces their compression rate when compressing only 1 gigabyte of data. We encode each neural network parameter with 2 bytes, using a float 16 representation since quantizing weights to this level doesn't significantly affect performance and is standard for model inference. We also note that further compressing the float 16 parameters using classical compressors doesn't significantly reduce their size. We also only consider the offline setting, which computes the adjusted compression rate using a 2-part code. In contrast, frequential, online, coding would provide an alternative view on adjusted compression by computing the adjusted compression rate as the log loss plus the size of the training script, not the model parameters. According to previous research, frequential coding leads to better compression with overparameterized neural networks, but it requires training the model online, which reduces performance and cannot be performed with foundation models, both during encoding and decoding, which is very costly for our models. Interestingly, chinchilla models, while primarily trained on text, also appear to be general-purpose compressors, as they outperform all other compressors, even on image and audio data. These models have not been trained on this kind of data, which consists of a mix of internet text data, Wikipedia, websites, GitHub, and books. However, it's still possible, but unlikely, that some images or audio samples were encoded into text on some websites. Thus, chinchilla models achieve their impressive compression performance by conditioning a meta-trained model to a particular task at hand via in-context learning. In contrast, smaller transformers, trained manually on NWIC 8, only achieve good compression rates on similar Wikipedia data, i.e., NWIC 9. However, larger models stronger in context compression, or in context learning, comes at a cost: the number of parameters, which has to be offset with increasingly large data sources when computing the adjusted compression rate. Finally, since chinchilla has been trained on Wikipedia, the NWIC 9 results are in distribution. Section Summary. The NWIC 9 dataset is a larger version of the NWIC 8 dataset, containing the first 1 billion byte of the English Wikipedia XML dump. It is used to evaluate a model's ability to compress data. The ImageNet dataset consists of annotated images used for image classification and object detection tasks. The Libri speech dataset is a collection of English speech samples derived from audiobooks. Comparing compression rates, language models suffer a significant loss in compression rate due to their large size, while general-purpose compressors like gzip perform well on a wide range of data sources. Chinchilla models, trained primarily on text, surprisingly outperform other compressors even on image and audio data. Section. Optimal model dataset size trade-off. Let's discuss the ideal balance between the size of a model and the size of a dataset. As we've seen, foundational models, which are typically hundreds of gigabytes in size and contain billions of parameters, can be quite costly in terms of compression rates. In an ideal world, where we have an infinite dataset, the size of the model wouldn't matter because it would be minuscule compared to the dataset. However, in reality, these foundational models only show significant compression rates when they're evaluated on datasets that are terabytes in size or larger. Given that this isn't feasible with typical hardware constraints, we've instead explored the optimal model size using smaller transformers trained on the NWIC 8 dataset. Remember, the size of the model, measured in bytes, is twice the number of parameters, assuming they're float 16 parameters. We've visualized the adjusted compression rate for various model sizes using the NWIC datasets. Our findings show that larger models perform better on larger datasets, which supports recent trends in model scaling. However, these larger models perform worse on smaller datasets, suggesting that scaling laws are dependent on the size of the test set. In other words, for each dataset, there's a critical point where the model size reaches a peak. After this point, the adjusted compression rate starts to increase again because the number of parameters is too large compared to the dataset size. It's important to note that we're evaluating offline compression, meaning we're not necessarily compressing the data the model was trained on. This means that the results on NWIC 7 and NWIC 8 are in distribution, while the results on NWIC 9 are out of distribution. Despite this, larger models still perform better on NWIC 9 than NWIC 8, highlighting the benefits of scaling. Let's now turn our attention to compressors as generative models. We've previously discussed how any compressor can be used as a sequence prediction model. To put it simply, for a given compressor, we calculate the probability of the next byte based on the length of the compressed sequence for all possible bytes. If a byte results in a particularly short compressed sequence, it will have a higher probability of being chosen next. However, generic compressors have a low inherent bias, so sampling data without conditioning doesn't yield interesting results as it appears random. Therefore, we condition the compressors on part of an existing sequence and generate the remaining bytes with the compression-based generative model. We've compared the generative performance of gzip and Chinchilla 70B across text, image, and audio data. There are two ways to evaluate generative models. One is by sampling the next byte using teacher forcing, which means conditioning on the true subsequence, and the other is via autoregressive sampling, which means conditioning on the model's previous outputs. The latter method can cause a distribution shift and unwanted side effects, but it's the standard method and the one we've chosen to visualize. Language models take a very different approach to compression compared to classical compressors. Classical compressors have a small program size and optimize for a large context length to exploit sequential dependencies in the data. On the other hand, foundational models consist of billions of parameters, which allow for quick adaptation in their relatively short context window. We've explored this phenomenon by visualizing the compression rate across sequence lengths for gzip, Chinchilla 1B, and a transformer pre-trained on NWIC 8. As you might expect, the longer the sequence, the more data the model can process in its context, and therefore, the better the compression. Transformers are typically not trained on raw input data but on tokenized versions of it, both for efficiency and performance reasons. As a result, transformers are trained on compressed data, with tokenizers acting as the compressor. Since tokenization is known to affect the generalization performance, we've investigated its impact on the compression rate. We trained transformers on NWIC 8 using different tokenizers. ASCII, which is an alphabet of size 256, no tokenization, and byte pair encoding trained on NWIC 8, with various vocabulary sizes. Note that the tokenizations are lossless. Increasing the number of tokens reduces the length of the sequence and thus increases the amount of information in a model's context. However, decreasing the sequence length comes at a cost. The number of tokens is larger, which makes the prediction task more challenging. In theory, as the tokenization is a lossless compression, the two effects should compensate. In practice, we found that if the model is small, increasing the number of possible tokens improves the compression performance. In contrast, for bigger models, having a larger token vocabulary seems to harm the final compression rate of the model. However, short sequence lengths also benefit transformers since their time complexity scales quadratically with context length, and they do not generalize well to long contexts. This explains why most practical transformer implementations still use some form of tokenization. Section summary. Foundation models incur high compression rates when considering their size, which is in the order of hundreds of GBs for billions of parameters. However, larger models achieve better compression rates on larger datasets, but worse rates on smaller datasets, indicating that scaling laws depend on the size of the test set. Additionally, tokenization has an impact on the compression rate, where increasing the number of tokens boosts compression performance for small models, but harms the compression rate for larger models. Section. Related work. We're going to delve into the related work in the field of prediction and compression, and how these concepts have been applied in various contexts. The relationship between prediction and compression is well established, thanks to Shannon's source coding theorem. Numerous methods have been developed that take advantage of this connection. For instance, context tree weighting, CTW, is a technique that combines the predictions of multiple Markov models to achieve lossless compression through a process known as arithmetic coding. Another method, prediction by partial matching, PPM, also uses arithmetic coding, but it creates probability distributions based on the history of characters in a sequence using a method called contiguous context matching. PAQ8, on the other hand, uses a combination of predictions from a large number of models, many of which are based on context matching. However, unlike PPM, PAQ8 also includes non-contiguous context matches. In a different context, researchers have shown how compression can be used to estimate the value of a policy in an environment. This idea was later expanded to include classification with compressors. This technique has been applied to natural language processing tasks, in combination with a k-nearest neighbor algorithm, and has yielded surprisingly good results with simple general-purpose compressors like gzip. Some researchers have taken this idea further by training the compressor on a large amount of unlabeled data first. Others have applied arithmetic coding to image compression, using mixtures of student distributions and Gaussian processes as predictors. Moving on to the use of neural networks in compression, previous work has shown that neural predictive distributions can be used to perform lossless compression via arithmetic coding. Neural networks have also been found to achieve strong lossless compression rates when arithmetic coding is replaced with asymmetric numeral systems. While these methods typically require a separate training set, some researchers have explored the use of arithmetic coding-based neural compression in a purely online setting, where the model is trained only on the data stream that is to be compressed. In terms of understanding the biases of neural networks, a lot of effort has been put into studying the biases of natural language processing, NLP, and transformers. For instance, a tokenizer for NLP-related research has been defined, which improves upon well-known techniques like byte pair encoding, BPE, BPE dropout, and subword regularization. In this paper, we demonstrate how these tokenization techniques can act as pre-compressors for the data, significantly influencing the final compression rates when paired with a neural model. We also discuss general studies on generalization, which we argue is equivalent to the model's compressive power when accounting for parameters' code length. Lastly, we touch upon the work done on compressing the neural model's parameters themselves.